Hi, this is Chen from University of Maryland. Today I'm going to present Distantly Supervised Evidence Retrieval enables question answering without evidence annotation. This is joint work with Chen Yan, Jordan, and Hao. Question answering has significant attention in both research communities and industries. Given an input question, in which city is Facebook located? Commercial search engines can directly predict the answer, Menlo Park. Also, there are several high-quality benchmarks that innovate models. Such a problem is often called open domain question answering. Most current QA systems have two steps, a retrieval step that finds relevant passages and a reading comprehension step that outputs an answer. Beyond simple questions, where the evidence is a single sentence, people also ask more complex questions like multi-hop questions. As shown in this example, we need to train in two evidence pieces. Facebook was launched at Harvard University, and Harvard University is in Cambridge. Commercial search engines often fail to answer them. Using the same framework, but now retrieve multiple evidence pieces as a train, state-of-the-art systems has good performance on benchmark dataset hotspot QA. However, answering multi-hop questions is still difficult. Look at this example. The correct evidence, the first passage of Wikipedia page, Facebook, and the Harvard University is given during training. This is helpful for training neural retrieval systems, which is a key component in the state-of-the-art QA system. But these annotations are expensive. For another single-hop QA dataset, natural questions, besides labeling evidence passages, additional annotators verify the correctness of the annotation. The situation is even more nuanced for multi-hop questions. To construct hotspot QA, to make sure multiple evidence pieces are used, a linked Wikipedia passages are pre-given and annotator write questions make sure that both evidence pieces are used. Obviously, this is not the most natural way to construct datasets. But what are you going to do? You need intermediate data, right? Even though previous work has found artifacts in the datasets. So, to mitigate this issue, we focus on a more general but challenging weakly supervised setting. We only have question and answer pair during training, and we leave the model to figure out the rest of them. We train QA systems that don't need intermediate evidence labels. What they need is a question, the answer, and figure out the rest. But to explain how our system works, we first need to talk about how normal open domain QA systems works. Then we introduce our method, which we call DistDR for short. Most current open domain QA systems use dense passive retrieval as a retriever. So given a question, a bird encodes them into a low dimension space. Another bird encodes the passages also in the low dimension space. Finding evidence requires us to take the similarity functions between the question embeddings and the passage embeddings. This could be done very efficiently via the approximate nearest neighbor search. Unlike fixed representations, these trainable encoders gives us lots of flexibilities to adapt to different tasks. For multi-hop questions, instead of looking for evidence once as normal QA, we take multiple retrieval steps to find multiple evidence pieces as a tree. After each retrieval step, we combine the question and already retrieved information into a reformulated query by appending the passage tokens to the question. Our reader is a bird reading comprehension model. The input is a question and evidence, which is a single passage for simple questions, and multiple passages for multi-hop questions. And it outputs a start and end span as the final answer. Now let's describe our proposed method, DistDR. This is a weakly supervised setting. We only have questions and answers during training, but we still need evidence somehow. To find evidence, we use distance supervision. We use a retriever to score relevant evidence for each question. Our intuition is that highly scored evidence by the retriever that contains the answer string is the positive evidence. This is because we hope the retrievers, although not perfect, could find some evidence that are semantically similar to the question. We also take inspiration from previous weakly supervised QA work for simple questions. For example, to find positive passages to construct the trivial QA dataset. They use BM25 to find top K, and usually the K is rather big, and use answer existence to find the positive passages. However, this does not work for multi-hop questions. This is because we cannot use term matching to find a chain of evidence pieces. Some evidence pieces in the chain contains little textual overlap to the question. For example, Harvard University is in Cambridge has zero textual overlap to the question in which city was Facebook launched. Term-based method like TF-IDF or BM25 simply fails. A natural choice is to use a dense retrieval model, which not only relies on the textual overlap, but it requires training labels. So we use dense retrieval, but take a different approach. We assume that which evidence is relevant is a latent variable to infer. To infer that variable, we use expectation maximization approach. We alternate between guessing which evidence is good and train new retrievers. But we need to start somewhere. So we start with the evidence finder that is pre-trained on other datasets, not multi-hop QA datasets. Then the process of iterative improvement begins. At each step, we use a current dense retriever to get a bunch of relevant evidence from Wikipedia. There are over 5 million passages, so we can only work with a subset. We guess on the good and bad ones, which we will detail in a second, and we call it hard E step. Then at M step, we update the model, assuming the evidence from the E step is the correct one. As shown in the figure, we hope at each iteration we could close the distance between the question and positive evidence in the low dimension space, which means we extract better evidence. And the better evidence could further help training the model. Okay, go through our DistDR with the example so we can detail how we separate the positive and negative evidence. The question is, which state is someone Chung works as a material scientist? To find the answer New Jersey, we need to train in multiple evidence. Someone Chung is a material scientist in Rogers University, and Rogers University is in New Jersey. At each step, our goal is to compute the most likely evidence. We use current dense retrieval to find the top K evidence, which is a single evidence piece for single hop questions, and a chain with two evidence pieces for multi-hop questions. Then we split them into positive and negative evidence based on whether the answer is in the evidence. This is good, but there's a problem. Using just answer matching can find some spurious evidence. For example, the foundation of Wayne also has the correct answer, New Jersey, but is not the correct evidence. To mitigate this issue, we use reader to filter out them. So, given a question and each evidence, we use the current reader to predict the most likely answer. If it does not match the gold answer, we filtered out this evidence. Then, at M step, we update our QA system with question, answer, and retrieved evidence. We evaluate this DR on two benchmarks, hop-hop QA, a multi-hop QA benchmark, and natural questions, a single hop QA benchmark. On hop-hop QA, our DistDR is slightly better than BeamDR using the same model architecture but on the fully supervised setting. On natural questions, DistDR is also competitive to fully supervised dense retrieval models, ANCE. So the takeaway is, with our DistDR model, we no longer need evidence labels to get on-par performance on various types of questions. We further conduct analysis on model behavior using hop-hop QA as an example. First, this figure shows training data statistics over the iteration. We can see the number of training examples increases over iteration, and the percentage of predicted evidence that match the gold one also increases. DistDR finds better evidence over iteration. Although DistDR is on par with fully supervised methods, on the last iteration, only 70% of the predicted evidence match the gold one. We want to study why. So we manually annotate 50 examples that the predicted evidence does not match the good one. 38% of the questions are answerable via single evidence pieces, so they are not actually multi-hop questions. For this example, the first evidence pieces already answer the question. Even though this DR does not find the correct second evidence pieces, it already finds the most salient training signals. In 28% of the question, this DR finds an alternate evidence. In this example, either of the movies The Mist and The Green Miles are the correct first evidence pieces. This DR finds another one which is good as well. And in last 24% of the questions, the evidence is incorrect. In this example, the evidence is incorrect, but as we can see, there's only one candidate that is a county name. So the reader makes the correct prediction for the incorrect reason. Having a faithful system is an important ongoing research direction. To summarize, we propose this DR, a dense retrieval-based QA system under weak supervision. It iteratively refines more accurate evidence and further encourages the model to this evidence. This DR is on par with fully supervised counterparts without using any intermediate annotation. Future work could focus more on more faithful QA systems that make correct prediction for the correct reasons. Also, different types of complex questions that require different reasoning abilities with weak supervision. Thanks a lot.